Hello everyone, welcome back to Electronics Prepper, the channel where we try to learn as much as possible about electronics to become more self-reliant with technology and prepare for the future. Today I would like to make a relatively quick video about interferences or what I would call parasite signals that appear in our circuits and that of course they are undesired. I'm specifically talking about parasitic signals that are being induced somehow from the power lines, from the 220 volt power lines that exist in our walls or in all sorts of cables around us. These sorts of parasite signals can affect pretty much any circuit to a certain degree, even if that circuit is not powered by a power supply connected to the wall, basically. Even if that circuit is powered by some batteries and it has no electrical connection whatsoever with the wall, these signals, these interferences will still appear in these circuits that we are creating. So I have made a few experiments and I will show you the results to better visualize this problem. So I have taken an op-amp IS358, which is the cheaper version of LeMet 358. It doesn't really matter. The op-amp in this particular case really doesn't matter. It's set up to be a buffer. Okay, so no amplification, no attenuation, no nothing. I'm powering it from plus minus 12 volts. Okay, so I have both positive and negative voltages to go so that whatever I have on the input is not a problem. And I am connecting the positive input, the non-inverting input, through a resistor to the ground, basically. Okay, and on the output I'm placing an oscilloscope to basically see the signal that I get to see. Now, ideally, we shouldn't really see anything, because if you think about it, you know, we have a buffer with its input connected to the ground. It doesn't matter that it's connected through a resistor. Worst case scenario, we should have a flat line at some voltage with some offset voltage, but other than that we should see a flat line ideally. Okay, in reality we will see that that's not really the case. And one important aspect that I think I forgot to mention: this resistor is not connected straight to the op-amp, meaning I haven't placed the wires of the resistor directly in the breadboard holes where the pin of this op-amp also is. Instead, I chose to connect it through a breadboard cable of 25 centimeters, which is longer than the usual short cables that you use to interconnect components on a breadboard. But I did so on purpose, because the longer the cables that we are using, especially on the breadboard, especially for the input or for the ground, the bigger these problems appear to be, and the easier it is for us to perform such experiments and to see some meaningful results. Okay, and this is particularly important because normally when we design circuits, you know, whether we write with a pen on paper or we are using such dedicated software, we are connecting components through simple wires, simple lines basically, and these lines for us mean a perfect conductor, right? A conductor that has 0 ohm resistance, 0 Henry inductance, and it's the ideal conductor. However, this is only on paper. In reality, we don't have ideal conductors. We must use at least cables initially, you know, on breadboards. We have to use some form of cables to connect components together. And in the end, when we create the circuits on a PCB or otherwise, it doesn't matter, we will have some form of wires or conductors or copper traces on an actual PCB, you know, that are also far from being perfect, far from being ideal. Okay, so like I said, in such a setup, we should see approximately 0 volts or a very small voltage on the output, and we should see no signal whatsoever. It should be a complete flat line. But in reality, this is not the case, and I've repeated this experiment for 5 different values of resistors. For 1 kilo ohm, 10, 100, 1 mega ohm, and 8.2 mega ohms. I would have chosen 10 mega ohms so that it's basically each resistor is basically 10 times bigger than the previous ones. But I just didn't have a 10 mega ohm resistor at hand. So I chose the highest value that I did have. And we will see that these parasitic signals basically form in our circuits. The more resistance we have, the higher the impedance it is, the higher this parasitic signal is, because these parasitic signals are weak. They are very weak. They don't have the power to generate big currents, so lower impedances will result in very small or even non-existing parasitic signals, whereas bigger impedances will allow these signals to exist. Okay, so let's get into the results. For the 1 kilo ohm resistor, on the output we see that we have something that kind of resembles a sine wave, at least if we, you know, imaginary draw a line at the middle of all this noise. Yeah, it kind of looks like a sine wave. We're going to measure peak-to-peak voltages from now on, just because it's easier and we can make comparisons easier. So here we have 1 millivolt per division, and we have, I don't know, 2.5 millivolts peak-to-peak, let's say. We're going to ignore these very sharp spikes. These are caused by probably by the switch mode power supply that is in my oscilloscope. Anyway, we don't care about that. We care about the bigger noise. So let's say about 2.5 millivolts peak to peak. Okay, for the 1 kilo ohm resistor here. Moving on, for the 10 kilo ohm, we see that we need to increase to 2 millivolts per division. And we have about 8 millivolts in total. Okay, because we have about 4 divisions. Again, we need to sort of draw a line at the middle of this entire shape on the screen. And that's mostly our parasitic signal. The rest is noise that can come from other sources as well. It is important to notice in all of these cases and the following that this signal has a 50 Hertz frequency. Okay, and don't mind this frequency meter in the corner of the screen. This many times will give false readings if the signal has a bit too much noise in it. This circuit will not be able to measure the frequency correctly. Okay, the best way of measuring the frequency is to basically count how many divisions you have per horizontal and calculate the reciproc of that, so 1 over how many milliseconds or microseconds you have. Okay, and like ignore this drawing that I did earlier with my hand. The signal here has 50 hertz because this is what I have in my wall, 220 volts, 50 hertz. Okay, this will become increasingly obvious in the next examples, so I will move on. 100 kilo ohm resistance or input impedance. Okay, I needed to switch to 10 millivolts vertically, and we see that along with these periodic spikes that also are probably from the power supply, we have about 3.5 divisions, so about 35 millivolts peak to peak, give or take. And if we move on forward with even higher impedance, then this parasitic signal becomes quite strong, quite well, I wouldn't say strong, but quite big. Okay, for 1 megohm we see that I needed to switch to 20 millivolts per division, and we have quite a lot. We have 20, 40, 60, 80, 100, 110 millivolts peak to peak of interference, of unwanted signal, give or take. And now it has become much clearer that we are dealing with a 50 hertz signal, right? Because if you take a full repetition of the signal, which is kind of from here to here, we see that it takes 4 divisions times 5 milliseconds, that's 20 milliseconds. 1 over 20 milliseconds is 50 hertz. Okay, so this clearly shows that this unwanted signal appears in our circuits because of the power in the wall, of the power cables in the wall. Now, if you live in America, or I believe in Japan as well, you will have 60 hertz here instead of 50. Okay, but here where I live we have 50 hertz, so yeah. And the final value, when I put 8.2 megohms for this resistor here, okay, we have the highest parasitic signal of them all, 200 millivolts per division, and oh boy, we have about 700 millivolts peak to peak of noise, of well, I shouldn't say noise, of interference, it would be more correct. And you know, the imperfect sine wave gets to be even more clear now, and also the 50 hertz frequency becomes even clearer. This is basically enough to turn on a bipolar transistor. Okay, 700 millivolts, yeah, would be enough to turn on a bipolar transistor, which, needless to say, it wouldn't be nice. So with this in mind, it's pretty clear that we ideally want to have as low input impedance as possible. Okay, sometimes that's not achievable, so we have to live with the consequences. Okay, when the impedance cannot be made smaller, we either have to think about perhaps using shielded cables between the part of the circuit that provides the signal and the next stage, the next circuit. Okay, perhaps we can use I don't know, coaxial cable or a shielded cable connected basically at both grounds, both from the previous circuit and to this circuit's ground. Or we just have to live with the extra interference that gets added on top of our signal, if that's possible. You know, if we have a DC voltage on the input, like we will have in a near future video, when I'll show you how I've built a device that sadly must have a high impedance on the input. Then we can use an RC low pass filter on the output and basically try to mitigate this problem, because my signal is just a DC voltage in my case. Okay, anyway, I don't have clear solutions. I don't think that clear solutions exist, so yeah, we just need to be aware of this problem, where it appears, how it appears, why it appears. Okay, like I've just explained to you, so that it doesn't catches us by surprise. Now, before I finish this video, let me show you a couple more things. So this is the circuit that I've created to perform all of these tests on the breadboard. In the middle you see this sort of like horseshoe cable, this half a loop created with that pretty long cable, 25 centimeter cable. That was the one basically picking all sorts of interference from the outside world, from the environment, and shoving it into my op-amp, so that my op-amp would, you know, pass it on the output. And if the op-amp would have been configured as an actual amplifier instead of a buffer, I would have seen a much bigger signal on the output. Okay, which is a bit of an ouch. So what I want to show you here in this video is that I was at some point just bringing my left hand closer, or taking it farther apart, farther away from this cable. Initially I wasn't touching the cable, and as you can see, this unwanted signal gets bigger the closer I get, because my body basically works like an antenna. And at some point I even touched this cable, just the outside insulator, and that's enough to make this parasitic signal even bigger. Okay, and create an even bigger problem for us. Other than that, I want to show you another video from this project that I was working on recently and that I finished, and I want to show you another case where this phenomenon can basically screw around with us. I had two circuits here, one in the middle of the screen. It was already built on a PCB, and one that I was testing on the breadboard. Okay, and these two circuits were connected between each other with relatively small wires, you know, thin wires. And even the ground was a thin and pretty long wire. And because the ground between these two circuits, right, was connected with this thin long wire, this interference would appear in this wire, and it would make it so that the ground of the breadboard circuit would not be exactly the same as the ground on the PCB, and therefore this entire circuit on the breadboard was functioning in a different way. Okay, and I was connecting something on the outside of the on the screen, but I was connecting the same thing every time. And initially, with this long ground wire, we see here on the breadboard that I have 10 LEDs. It's basically a VU-meter. Okay, and I was having all of these LEDs turn on. Okay, like you can see here, in spite of the fact that I shouldn't have had it. But again, because of these parasitic signals that were induced or coupled into my ground wire, the second circuit was seeing a much bigger input signal than it should have seen. Okay, and when I took a much shorter and thicker cable and I connected these two grounds more directly, essentially bypassing that long and thin ground wire, when I was connecting the same exactly the same thing on the outside, I was only getting 6 LEDs turned on and the other 4 were remaining turned off. And this was the actual behavior that should have happened at all times. Okay, so this clearly shows how even the ground wires can be affected by this sort of interference, and why is it so important that we know about it, that we are aware of it. Okay, so that's pretty much it for this video. Thank you very much for watching it. I hope you learned something new and it was interesting and useful for you in the future. Please like and subscribe to the channel if you want to see more of my videos. Also, please consider supporting my work on Patreon. The faster I can buy components and lab devices, the faster I can learn things, and the more I can come here on YouTube to show you, so that you don't have to spend so much time and energy, so that you can just learn from me directly. Thank you very much, and I will see you in the next video. Bye bye.